The birth of the solar system. Around 4.6 billion years ago, our solar system did not exist. Instead, there was a vast, cold cloud of gas and dust known as a solar nebula. It floated through the Milky Way galaxy, silent and dark. Then something disturbed it, possibly a nearby supernova explosion. The cloud began to collapse under its own gravity. As it collapsed, it spun faster. It flattened into a disk. Most of the material gathered at the center. That center became the sun. Over time, particles collided. They stuck together. They formed rocks. Rocks became planetesimals. Planetesimals merged into protoplanets. And eventually, planets were born. This process is known as the nebular hypothesis, the leading scientific explanation for the formation of our solar system. Part 2. The structure of the solar system. Our solar system is organized in layers. At the center, the sun. The sun contains 99.8% of all the mass in the solar system. It is a massive nuclear fusion reactor, converting hydrogen into helium and releasing enormous energy. Orbiting the sun are 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The inner planets are rocky. The outer planets are gas giants and ice giants. Beyond Neptune lies the Kuiper belt, filled with icy objects, including Pluto. Farther still is the Oort cloud, a distant shell of icy bodies that may stretch nearly halfway to the next star. Part 3. How the solar system works. Everything in the solar system is governed by one force: gravity. Gravity is the invisible glue holding everything together. But how exactly does it work? In 1687, Isaac Newton published his law of universal gravitation. F equals G backslash frac M underscore 1M score 2 R squared. This equation says, every object attracts every other object. The force increases with mass. The force decreases with the square of the distance. This explains why planets orbit the sun, moons orbit planets, tides rise on Earth. But gravity does more than pull, creates motion. Planets do not fall into the sun because they are moving sideways fast enough to keep missing it. This balance between forward motion and gravitational pull creates an orbit. An orbit is not random. It follows precise mathematical laws. Part 4. Kepler's laws. The geometry of motion. Before Newton, there was Johannes Kepler. Using data collected by Tycho Brahe, Kepler discovered 3 fundamental laws. He kept 1 planets move in ellipses. The sun is not at the center, it sits at one focus. He kept 2. A line from the planet to the sun sweeps equal areas in equal times. This means planets move faster when they are closer to the sun. Keycap 3. The square of a planet's orbital period is proportional to the cube of its distance from the sun. T squared backslash propto r cubed. This simple relationship allows astronomers to calculate orbital periods precisely. Mathematics revealed that the solar system is not chaotic. It is predictable. It is structured. It is a cosmic clock. Part 5. How we discovered the solar system. For thousands of years, humans believed Earth was the center of everything. This model is called geocentrism. Then came Nicholas Copernicus in the 16th century. He proposed heliocentrism, the idea that the sun is at the center. It was revolutionary. It was controversial. Changed history. Later, Galileo Galilei used a telescope to observe the moons of Jupiter, the phases of Venus, craters on the moon. These observations proved that not everything orbits Earth. Then came Newton. Then Einstein. With Einstein's theory of general relativity, gravity was no longer just a force. It was the bending of spacetime itself. Mass tells space how to curve. Space tells objects how to move. The solar system is not simply spinning in emptiness. It is moving through curved spacetime. Part 6. The mathematics of stability. The solar system appears stable. But why does it not collapse? Why do planets not collide? The answer lies in conservation of momentum, conservation of energy, orbital resonance. For example, Pluto and Neptune never collide because they are locked in a 3:2 orbital resonance. Jupiter's gravity stabilizes some regions while destabilizing others. The system behaves like a complex gravitational dance. Even small changes in mass or velocity could alter the entire structure. Scientists use advanced mathematics and computer simulations to predict planetary motion millions of years into the future. The solar system is stable but not forever. Part 7: Chaos and Future Evolution. The Sun is currently in its main sequence phase. It fuses hydrogen into helium, but in about 5 billion years, hydrogen will run out. The Sun will expand into a red giant. It may engulf Mercury, possibly Venus, maybe even Earth. After that, it will shed its outer layers and become a white dwarf. The planets that survive will drift around a fading star. The solar system will change forever. Part 8: Exploration and Modern Discovery. We have not only observed the solar system, we have touched it. The Voyager probes left the solar system. Rovers explore Mars. Spacecraft orbit Jupiter and Saturn. We have landed on the Moon. We have sent machines beyond Pluto. Using spectroscopy, radio waves, and space telescopes, we analyze planetary atmospheres, magnetic fields, chemical compositions. The solar system is no longer just something we see in the sky. It is something we explore. Part 9: Why it Matters. The solar system is our home. Protects us. Jupiter acts as a gravitational shield against many asteroids. The Moon stabilizes Earth's rotation. Without this precise arrangement, life might never have formed. Understanding the solar system helps us predict asteroid impacts, understand climate cycles, search for life beyond Earth, discover exoplanets around other stars. When we study our system, we learn how other systems might work. Final scene: the bigger picture. The camera pulls back. The Sun becomes just another star. Our solar system becomes a small dot in the Milky Way. And the Milky Way is one galaxy among billions. Yet inside this small system, on one small planet, conscious beings emerged. Beings capable of understanding the equations, of mapping the orbits, of asking how it all began. The solar system is not just a collection of planets. It is a story of gravity, time, mathematics, and curiosity. From dust to stars to minds that can comprehend the cosmos. And the story is still unfolding.